Now in Calculus 1, we learned how to evaluate limits. If I have the limit as x approaches a particular value and I can evaluate my function at that value, I would do so. But if I try to insert value 2 into there, I would get numerator and denominator both tending to 0. Now 0 over 0 isn't a value, it's what's called an indeterminate form. So we'd say this quantity approaches this form, which means I can't answer the question. In fact, it means this question is actually interesting. Now, based on the fundamental theorem of algebra, if 2 makes the polynomial equal to 0, then x minus 2 has to be a factor. So I can easily factor this. Even if I wasn't very good at factoring, I already know I have this right here. Now on top, I'm going to have 2x squared minus 3 on the bottom, x plus 3. Now at this point here, I can factor and I can cancel. I can't evaluate yet because I'm still 0 over 0. What I'm going to do is eliminate the part of the problem that's causing the issues. X equals 2 is what's called a removable discontinuity because I am removing it from the problem as a discontinuity. Right now, this quantity can easily be evaluated at 2. So if I replace numerator and denominator with 2, I'd get 2 times 2 squared minus 3, that's 5. 2 over 3, 2 plus 3, and so my final answer would simply be 1. Now let's consider the following limit. I'd like the limit as x approaches 1 of this quantity. This time it is not an indeterminate form because my numerator is 1 and my denominator is approaching 0. We call this an asymptotic form, and the graph would actually look something like this. Now, whenever you're looking at an asymptotic form, you have to consider the left and right-hand limits. So we'd start this problem by looking at the limit as x approaches 1 from the left of 1 over x minus 1, and the limit as x approaches 1 from the right. Now, as I approach 1 from the left, my denominator is approaching 0, that's true. But 0 from which side? As I approach 1 from numbers to the left of 1, then x minus 1 is approaching 0 from the left of 0. That means that I am growing without bound negatively. So this first limit here would be negative infinity. Here, as I approach 1 from the right, then x minus 1 is approaching 0, but from the right. Now I'm going to put brackets here to indicate that it's not a number, but a form. Form, think about it as dictating strategy. So in this case, I am growing without bound, but positively. So this limit is positive infinity. Evidenced by the graph, as I approach 1 from the left, my y values are descending forever. As I approach 1 from the right, I am raising forever. Although you never need a graph in order to calculate a limit, sometimes it helps us understand. Because the left and right limits were not the same value, overall we would say this limit does not exist. Now I want to remind you, when it comes to limits, there are only 3 possible answers. A limit is finite, a limit is infinite, or a limit does not exist. Now let's look at a 3-dimensional problem here. I would like the limit as my ordered pair approaches this point. Another way of thinking about this is a 3-dimensional problem. This is a surface, and I am approaching a particular point on the xy plane, which will be my floor. What is my z value approaching as I do this? Now, if I replace x and y with 1 and 2 here, like before, I will get the indeterminate form 0 over 0. But unlike before, this is not a simple factor and cancel because I have 2 variables. But I can still attempt to factor this in a different way. Now, before you start thinking, oh, I can just use L'Hopital's rule like we did in Calc 2, remember a very small percentage of limit problems, even in Calculus 1 and 2, can be done using L'Hopital's rule. But L'Hopital's rule will no longer work because it only works with 1 independent variable. It won't work with 2. So factor and cancel really is the only way we can do this. So if I factor the numerator, because they are just quadratics, this will be 2x minus y times x plus y over 2x minus y times 3x plus 2y. My problem child, the part that was going to 0 are these terms right here. So if I factor and cancel, that will leave me with something of the form x plus y over 3x plus 2y. I couldn't evaluate this yet because it's still 0 over 0. But at this point, I can evaluate this quantity because neither numerator nor denominator approaches 0. Now my numerator is going to approach 3. My denominator is going to approach 7, so my limit is simply 3/7. So you see, the way we attack this problem is very much like the way we did it in Calculus 1. So when I can factor and cancel, I will. Now let's look at an example where that won't work. Now let's consider the following problem. Once again, as x and y both approach 0, numerator and denominator will both tend to 0, so we get the indeterminate form 0 over 0. Now in Calculus 1, almost every time we got something like that, we felt we could factor and cancel and finish it. But in this case here, numerator and denominator go to 0, but nothing's going to factor and cancel here. So I have to try a different approach. Now, earlier when I did the problem with the vertical asymptote, we looked at the left and right limits, and we said when the left and right limits are not the same, that means the limit does not exist. Well, on a number line, you can only approach from two directions. So that's why we talked about left and right limit. Now we're looking at the entire xy plane as potentially the domain, so all paths to 0, 0 have to yield the same answer. So the simplest way to attack this problem is to choose a path that gets us here but passes through infinitely many values. So we're going to choose the path y equals mx. This is the simplest of all paths. It's not the only one, but this is every line that passes through the origin. Every value of m gives me a different line. Now, I could have said y equals mx squared or mx cubed or m times the square root of x. There's an infinite number of paths that pass through the origin. I just need to show that more than one path leaves me with different answers. So we're going to continue this problem along this path. So that will yield x comma mx approaching 0, 0 of 6x squared minus 3 times mx quantity squared over x squared plus mx quantity squared. Now at this point, if x comma mx is approaching 0, 0, that's the same as simply saying x is approaching 0. So this will be equal to the limit as x approaches 0. Now if I simplify that quantity, I'll have 6x squared minus 3m squared x squared over x squared plus m squared x squared. And I notice that I can factor out an x squared out of top and bottom, and that would leave me with 6 plus 3m squared, and then x squared times 1 plus m squared. Now, the x approaching 0 was the problem, and I can now rid it from the problem. So that will leave me with just the limit as x goes to 0 of 6 plus 3m squared over 1 plus m squared. Since m represents the slope, m is a constant, and we know the limit of a constant is the constant. So I get as my final limit this quantity here. So we said if we approach the origin through any line passing through the origin, then our limit will be this. It gives the illusion that this is our answer, but actually there's an infinite number of choices I could have for m. Every value I choose for m will give me a different answer. For example, if I choose a slope of 1 along the line y equals x, this would be 9 over 2. But if I chose m equals 2 along the line y equals 2x, I'd get 6 plus 3 times 4, that'd be 18. 1 plus 2 squared, that'd be 5. That would be a different limit. Every value of m gives us a different limit. Therefore, the overall limit does not exist. The reason? Different paths give different limits. Similar to Calc 1, where when we approach from left and right, we didn't get the same value. Now we're saying, I'm approaching from a different direction, and I got different answers. So there's two types of limits that we address. One where we know we can evaluate it, and therefore we try to factor and cancel, or one where we don't believe we can, in which case we try to prove it doesn't exist by choosing a path.